what I want to do today, one of the things I want to do today is continue and tell you about Coulomb's experiment in magnetism, where he determined the force law for magnetism that was somewhat like the force law we've seen him determine for electricity. But before I go into that, I want to say a few things about mathematics first, because I think there was some confusion at the last class. And the reason there was confusion is because I was going through the steps quickly without really explaining them, and some of you missed all that business about manipulating all those mathematical proportions that I was talking about last time. And I'm sure that because I did it fast and didn't explain it, it seemed complicated. Well, I want to try to prove to you today that it's not complicated at all. So let's start with that. So this first section you can entitle Equations and Proportions. Now, let me just start out going back to a couple of simple equations that those of you who were here last year saw when we studied Galileo. Remember, one of the things Galileo did was he discovered the law of free fall. Remember, he discovered how fast things accelerate when you drop them. Okay, now does anybody remember what that number was for acceleration? So many feet per second per second. Evan?
32.
32. Right, so the equation that number pops up in is the equation for the speed of the object. If you what Galileo said was the speed, let's say we symbolize that by v, is equal to 32 multiplied by the time in seconds. So this is the speed in feet per second, and this is the time in seconds. So, that simple equation tells you that, well, after 1 second, how fast is the thing going? 32 feet. Yeah, 32 feet per second. After 2 seconds, it's going 64, right? True. No, it actually doesn't. That's one of the great question. That is one of the things Galileo discovered, was that it doesn't matter at all how heavy it is. You can take a wooden ball and a lead ball, okay, that drop them both from the same height, and they'll hit the ground at the same time. True.
That's anything, right?
Anything.
What about like a feather?
Absolutely. In fact, they do this demonstration in physics classes. Now, you have to do it. The difference between the lead ball and the feather is the lead ball is pretty much unaffected by the air. The feather, on the other hand, is impeded by the air resistance. But if you take away the air, okay, if you put them both, let's say you have a big glass tube and you've pumped all the air out of it, and you drop them both, the lead ball and the feather, inside that glass tube, you'll see both of them hit the ground at the same time. It's a remarkable demonstration. It's just shocking to see a lead ball and a feather fall down together. But we don't have that apparatus here at Van Damme Academy, but Maybe you'll see it when you're a freshman in college. Now, but this is the equation that Galileo shows applies to all objects in free fall on the surface of the Earth. Now, this number 32 is actually not a number that Galileo even had, because he didn't use these units of feet and seconds. So you can see that it depends on the units what exact number you get here. For instance, if we were to measure speed in meters per second rather than feet per second, what do you think would happen to this number? Troy?
It would go up. Well, no. It would
Go
down.
up? Down, right? Because how many, let's say after 1 second, okay, the speed is 32 feet per second according to this equation. Well, how many meters is 32 feet? Turns out to be about 10. Okay, so at the speed after a second is 10 meters per second, which is equivalent to 32 feet per second. So, this number depends on the units that you use. Okay, but what is always true, okay, in any units you choose, is that the speed is proportional to the time. Okay? And you can write that using this symbol that I introduced last class. And that symbol just means proportional. Now, what does that mean? It just means that if you double t, you double v. If you quadruple t, you quadruple v. If t is half, v is half. So they vary together that way. That's all that means. Okay, now Galileo discovered another equation, the equation of pendulums, and I wrote that, well, I didn't give you the actual equation, I just gave you the proportionality last time, but we can write Galileo's equation in that way. Again, using units of feet and seconds. It turns out that the period squared of the pendulum is equal to 1.23 times the length of the pendulum in feet. Yes, Daniel.
Get 1.23.
How do you get it? Galileo got it just simply by doing measurements. He made a, let's say you want to build a pendulum that has a period of 1 second. Okay? Well, he can just find out how long does the pendulum have to be in order to get a period of exactly 1 second. Well, if you do that, you find out that it has to be about roughly 0.8 feet, or right around 10 inches. So, less than a foot. So that if L is 0.8 here, and you multiply the 0.8 times the 1.23, you get 1. Okay, so it works out. And you can just, so that's how Galileo got it, was just by seeing, he could measure L, and he could measure T. And he found out, just experimentally, that the constant relating them was this 1.23. Troy?
Wouldn't that depend on where he was doing the experiments? That number?
Yeah, it would. That was the next step that Newton took, was to figure out that this isn't all there is to this equation. The equation that Newton came up with was that crazy looking equation. This is, and so Newton's equation does something that Galileo's equation doesn't do. It tells you how the pendulum, the operation of the pendulum actually depends on the strength of gravity. Dan.
Is it 4 pi squared L over G, or is it 4 pi squared times L over G?
Oh, two are equivalent.
Excuse me?
The two are equivalent. There's no difference between, the question is my equation this, or is it this? Pick which one you like. Nick. Okay.
When you're talking about
Right.
a 1 second pendulum, is the 1 second how long it takes to swing to one side, or it takes to swing back and forth?
Oh, back and forth. A complete cycle. Okay. Now, if I were to write this equation in terms of a proportionality, what would I write? JJ. I mean, if, see, what a proportionality does is it abstracts away from, I mean, it ignores the specific constants involved and just states the relationship between the two things that can vary, okay, that can change. So when you state it as a proportionality, you're just saying how, in this case, the length of the pendulum varies with the period of the pendulum.
Oh, it's proportional to t squared.
Yeah, so all you do is, and this is the way I was stating it last time when I did the last class when I did the mathematical manipulations. I was writing that equation of Galileo's just as t squared is proportional to L. Now, I was doing that because for what I was trying to show you, all that mattered was how the two were related, and the constants didn't matter, so I didn't want to carry them around and write them down. But you can see that, I mean, I could have written everything in terms of equations last time. It would have looked more complicated because I would have had to carry around all these constants, okay? But don't be, I'm just trying to get you to not be thrown off when I use this symbol. Because there's nothing, you do more complicated stuff than this all the time. That math that we did last time, I mean, if I'd explained it right, is 100 times easier than your literature class, for instance. I mean, I sat through some of your literature class the other day when you were discussing the interpretation of El Cid, and that's much more complicated than mathematics. Mathematics is a piece of cake. Now, okay, now Troy had asked about, well, you know, is Galileo's equation, you know, always right? Well, no. Galileo, of course, did all his experiments on the surface of the Earth, and he never really considered how his pendulum might be affected if the gravitational force actually varied. Newton did consider that question, and he had to fill in what this constant actually means. Now we can see, on the basis of what Newton knew, where Galileo's constant actually comes from. If you multiply 4 times pi squared, turns out you get something close to about 40. Okay? This number is the acceleration due to gravity, which is on the surface of the Earth is 32 feet per second squared. Okay. Well, what do you get if you divide 40 by 32? What?
1.23.
Something really close to it. Yeah. I mean, this number is a little less than 40. Basically, if you take these two numbers and you do the calculation, you get Galileo's 1.23. Okay. Now, the way I was writing this equation last time, Ben, in terms of a proportionality, how would you write that one? T squared is proportional to, well, it's proportional to L. Now, from a Newtonian perspective now, where that this acceleration due to gravity, okay, might change if we're not always the same distance from the center of the Earth, right? If we go on top of a mountain, or last time I talked about blasting off into a spaceship. So if we want to keep that in the equation, keep track of how the period of the pendulum will vary with the strength of gravity, then we'd write this like that, right? All we do is, see, we just drop off the things that we know are going to be constant in the case that we're considering. And obviously, 4 pi squared is always a constant. So that, so this tells you, this just states how things, what the period of the pendulum depends upon in terms of what things can actually change that will affect the period. And it's the length of the period and the strength of the gravitational pull. Okay, our proportion is starting to look less mysterious. Christopher, does this make sense? I mean, I just want to get to the point where this symbol doesn't throw you off, and you can just follow the kind of manipulations that we did last time. Now, let's just to go into to repeat a little bit of what we did last time. Remember, I asked you the question of, the Galileo, of course, always had his pendulum right down on the surface of the Earth. And last time I said, well, what if we blasted off in a spaceship 4,000 miles up here and had our pendulum up there? What would happen to it? And so we have this proportionality that we're working with. Now, G, what do we know about G? the gravitational acceleration. Troy.
It falls off with the square of the distance.
Yeah, but rather than starting out writing it, that's what I did last time. I just said it's proportional to 1 over r squared. But let's start out with an equation first. What is G exactly? Neve.
The force pulling things down.
Yeah, I mean it's the acceleration, not the force is the acceleration multiplied by the object's mass. Here I'm just focusing on the acceleration. The equation for the acceleration where big M here is the mass of the Earth. And r is the distance.
What is that below the M?
E.
Oh, I just called it m sub e because it's the mass of the Earth. Yes, Troy.
Well, doesn't it include both masses in the equation?
For the force, not the force on this object depends on its mass, but its acceleration doesn't depend on its mass at all, right? That was Galileo's discovery that all things, independent of their mass, fall at the same rate. Okay, it does depend on the mass of the Earth. I mean, if this were the moon rather than the Earth, then this object wouldn't fall nearly as fast, right?
That's because the force to move it cancels out with the force.
Yeah,
With the mass that you have.
Right, exactly. From last year, I talked about how the it takes more force to move an object with a bigger mass, right? You have to push on it harder. Okay. But an object with a bigger mass actually attracts more gravitationally. So those two things cancel each other out. That's the explanation for why the lead ball and the feather actually fall at the same rate. Okay. So now in this case that I talked about last time, I mean, we're not going to vary the mass of the Earth, right? We tend to leave that the same. And this G here is just a constant. That never changes. So that's why I could ignore those terms last time and just say G is proportional to 1 over r squared. Because the only way we can affect this acceleration due to gravity is by moving it closer to the Earth, in which case it gets bigger, or further from the Earth, in which case it gets smaller. But the only thing the way we can change this magnitude of the gravitational acceleration is just by varying the distance.
What is big G?
What is the number? It depends on the units that you use, but if you use meters and seconds and kilograms, the number turns out to be 6.67 times 10 to the negative 11th. You asked. It's a real small number.
Yeah.
Which is interesting in itself, actually, because it has to do with the fact that the gravitational force is actually pretty weak. Well, I'll say a little later, I'll actually tell you a little bit about comparing the strength of the gravitational force with the strength of the electrical force. And Electricity is surprisingly strong compared to gravitation. Okay. So this is hopefully you can now understand why last class I wrote this peculiar equation.
Oh yeah.
That the only way that this gravitational acceleration is varying is with distance. And this is the way it varies with distance. You know, it goes as 1 over r squared. Okay, so, and then with, everybody knows, JJ, when I write this, you know I can multiply the denominator and the numerator by r squared. And what do I get in the denominator? Multiply this by r squared. Yeah, you just get 1. Multiply this by r squared, I get r squared L. Okay. Right. Now, the upshot of this whole thing last time was Coulomb has an idea for a different kind of pendulum. Right? His electrical pendulum, he charges up some sphere, and then he has a pendulum of fixed length on a pivot with a little negatively charged object at the end of it. And because, now, well, what is L in this case of Coulomb's electrical pendulum? Neve?
The length between the pivot to the ball.
Between, oh, what, this?
Yeah.
Oh, absolutely, yeah, exactly right. That is L. Okay, are we varying that? No. Coulomb never changes it. So in his case, L is just constant. Now, what is the thing that Coulomb's varying? Daniel?
Distance.
The distance.
From the I think it's the ball you said, and then
Yeah.
the sphere and the ball.
Yeah, the middle of the sphere to his charged ball over there, that R, okay? That is what he's actually varying in this experiment. So what he's interested in is how does R vary with, and what is he measuring here? Ben, with this setup, what does Coulomb do now? And what does he actually measure?
The force.
Well, I mean, this is his electrical pendulum experiment. So what is he going to do? He's going to push this thing to the side, right? And he's going to watch it flip back and forth. And what's he going to count?
How many times or how many seconds it takes?
Yeah, right. How many seconds? I mean, what he ends up calculating is how many seconds it takes for the thing to swing back and forth. In other words, the period of this pendulum. And then he's going to set the pendulum at various distances from the ball and see how that period is affected. So he's going to see how t depends on r. Now, what actually came out of that experiment, when he doubles r, what happens to t? Nick?
T is cutting a fourth.
Oh, you're thinking it's an inverse square relation. No, not in this case. There's an inverse square relation involved, but it's not between t and r. Evan?
If he doubles t, or if he doubles r, he doubles t.
Right, that's exactly what he finds, that t is proportional to r. That's the result of his experiment. Now, what does that imply about the relation of the electrical force to r? In other words, this is his actual experimental result. But what does that mean in terms of the strength of this electrical force? I mean, electrical force is what's causing this pendulum to swing back and forth at all, right? It's pulling this negatively charged ball toward this positively charged sphere. And that's what's causing it to swing back and forth. And what Coulomb really wants to know, I mean, he doesn't really care about the relationship of t to r so much. What he really wants to know is, how does the strength of this force depend on distance? Okay, so this is what he's got. What does that tell him about how the force has to depend on distance? It's all up on the board. Well, this equation that Coulomb gets from his experiment is exactly equivalent to this equation we see up here, right? I mean, what we got out of this was t squared is proportional to r squared. The same thing as t is proportional to r. Right?
Yeah.
Okay, so, but how did we derive this equation? By assuming that, I mean, we were talking about gravity here originally, but this is the acceleration due to the gravitational force. We said, well, that depends, that's an inverse square law. The gravitational force falls off as the inverse square of the distance. And that's how, and that leads to t being proportional to r. Okay, if the force falls off as the inverse square of the distance, t will be proportional to r. Well, that's exactly what Coulomb finds for electricity. Evan, did you? Or I just said what you were going to say? Or,
Kind of.
okay.
It means that magnetism has to.
Well, this is still, yeah. So here we assumed that the force was fell off with the square of the distance, and we can get this equation out of it. And then this is exactly what Coulomb finds when he does the experiment. So that the force must be falling off as the inverse square of the distance. Now, when I say force falling off as the inverse square of the distance, I hope that that isn't just a bunch of words to you, that you realize that, oh, that means if I double the distance, the force goes down by a factor of 4. Remember what this, those aren't just symbols. In reality, they mean, I double this distance, if this distance is, if I double this distance, obviously this side of the proportionality goes down by a factor of 4, right? Which means the force goes down by a factor of 4. Okay, so the bottom line here is that all this, what I'm doing, when I work with these proportionalities, and this probably won't be the last time we see them in this class, all I'm doing is simplifying things by omitting numbers which are held constant, you know, in a particular situation that I'm considering. Okay, so I mean, you can always eliminate these proportionalities and write everything in terms of equations, but it means you have to carry all these constants around, like the mass of the Earth and the gravitational constant and 4 pi squared and all that stuff. Okay, so nothing mysterious about this. It's just algebra. Okay, so let's continue. I want to now go back to Coulomb's experiment on magnetism. Trying to measure the strength of magnetic forces. And remember what he does here. His idea is he's going to have a little magnet, say, there's the North Pole and there's the South Pole. And then he's going to bring up some big old long magnet. And he's going to hold this magnet in a fixed position. He's going to put this one on a little pivot and let it swing back and forth. So now he's got a magnetic pendulum. And then what is he, I mean, why is he doing all this? What does he want to know? Neve.
How the force, if the force of magnetism is indirectly proportionate to the distance squared.
Yeah, inversely proportional to the distance squared, right. So what does he want to do? I mean, he wants to move, I mean, he wants to have this magnet in a certain fixed location so that he knows this distance. Let's again call that R, just to stay consistent. The distance from the middle of the pivot on this short little magnet and the pole of this long magnet that is supplying the magnetic force on this little guy. Now, this south pole, of course, is being attracted to this north pole, which is why the little pivoting magnet is going to swing back and forth like a pendulum. Now, in this case, what Coulomb actually measures is the frequency of this pivoting little magnet. So, in other words, he will measure let me see what. Well, I'll go ahead and give you the data that Coulomb came up with in this experiment. Evan.
Were you gonna tell us how he eliminated the Earth's?
Yeah, I'm going to get to that in a minute. I'm doing it in a little bit different order today. Okay, so here's what Coulomb actually comes up with when he does this experiment. His first he first brings this long magnet of his up to a distance where R is 4 inches. And he finds that the frequency, in other words, the number of oscillations per minute of this little magnet is 43. Okay. Then he doubles the distance. Finds that, well, what's going to, actually I should ask you. What's the next frequency number that you expect? I take guesses now. I mean, you can't possibly get this right, but just take a guess. I mean, is it going to go up or down? First of all, that's the first question. Troy.
It'll go down.
Down, right. The force, obviously, you've doubled the distance now. The force is getting weaker, which means that it's going to oscillate more slowly, right? So it has to go down.
By how much?
By how much? That's the question. Coulomb didn't know himself.
It can't be an even number, can it? I can't go down evenly. Like, say if it went down by half, it would probably not be a decimal number, right?
Well, it might go in half. You've doubled the distance. Would it go in half? Well, it turns out it doesn't go quite in half. It goes down to 25. Now I'm going to give you one more piece of data. And he doubles the distance again. 7.
Because it's down 18 again.
Yeah, no. Oh, that, okay. No, it turns out that's wrong. It's a valiant try, though. 18 had something to do with it. It goes down to 18. Now this is the raw data from Coulomb's experiment. And it's not clear at this point what to make of this. And, but we'll see next time that this data actually implies an inverse square law. It's impossible to see that at this point, but I will. It's like pulling a rabbit out of a hat, and I'll do that next time. Evan, did you?
This data, he still hasn't done any calculations with the Earth or.
Right. He hasn't done a couple of things here. First of all, this isn't what we want, frequency. We want force. So he has to relate the frequency to force, and he has to account for and subtract the effect of the Earth's gravitational field. So he's got some work to do.